Thank you very much, Kevin. And yeah, thank you very much to the organizers for putting together this very nice workshop and for inviting me and having me here. This is really a great pleasure and honor for me. So today I will talk about a topic that I've been working on for a while, that is topological derivatives. And in particular, we'll focus on situations where it's not possible to obtain closed form formulas. So that includes quasilinear PDE constraints and the case where you have non-standard inclusion shapes. But I will come back to that in a second. And in that case, I will talk about how to numerically approximate topological derivatives and to use them in certain applications. As my outline, I will begin with a brief introduction of the topological derivative concept. Then I will go through the main steps of computing topological derivatives as it is done in well understood problems, let's say. And in particular, we'll show how this approximation step will be realized. And finally, I will show applications from topology optimization from electromagnetics. My favorite application is optimization of electric machines. So we will see that, and also an application from mathematical imaging. Let's start. Topological derivative. I think we haven't heard about this concept at this workshop yet. So I will take some time to introduce it. So imagine you're given, say, a hold-all domain D and a subset omega, and a cost function J that depends on the shape omega, so a shape functional. And then we're interested in perturbations of this shape and how this affects the cost function. So imagine we're now perturbing the domain omega by introducing a new component in the other subdomain, or we could also say we perturb the blue domain by introducing red material around a fixed point z. So we choose a fixed point z in either the red or the blue subdomain, and we introduce a perturbation. We introduce an inclusion. We call it omega eps of z. That is an inclusion that is centered at the point z, is of radius epsilon, and its shape is given by this little omega. So typically, you may think of disk shapes, like ball shaped inclusions, but today we will see that you can also deal with other inclusion shapes. So given this notation, we define the perturbed domain, omega eps of z, which in this picture would be the now red subdomain. And now we're interested in how does this topological perturbation affect the cost function value. So we look at the difference of the perturbed and the unperturbed cost function value divided by the volume of the inclusion, and the limit for epsilon going to 0 gives us the topological derivative. We see already from the definition that whenever the topological derivative is negative at a certain point, that means that in introducing that inclusion will give a decrease of the objective function. That's the kind of information you often use in optimization algorithms. And just as a remark, here's an alternative definition. You can also write it in terms of a topological asymptotic expansion of the cost function. And then the first order topological derivative would be the first term here. L1 of epsilon is typically the volume of the ball or of the inclusion. And this way you can also define higher order terms, higher order topological derivatives, which we also will see later on. Okay, topological derivatives find application in different areas of applied mathematics, say, for instance, in inverse reconstruction problems, when you have a body where you know that some inclusion of a different material is inside and you have some measurement data, say UD, for instance, on the boundary, then you can solve a problem as is depicted here, and your topological derivative shows you where that inclusion is if you have enough data and if the problem is nice enough. So that's one example. Another example is mathematical imaging, which I will come back to at the very end of my talk. And other, maybe the largest application region is iterative optimization algorithms, as we see here, but also this will be, we will see again later. Okay, so yeah, if we want to deal with this topological derivative, we should have a way to keep track of it, to access it. So there exist closed form formulas for a large class of PDE-constrained topology optimization problems, in particular if the PDE constraint is linear or semi-linear, and only under the assumption that the inclusion shape is either a disk or ellipse in 2D or a ball or ellipsoid in 3D. If both these assumptions are satisfied, you can compute closed form formulas of the topological derivative only involving the solution to the state and the joint equation. However, if one of those two assumptions is not satisfied, this is not possible so easily anymore. And this is the case which we want to address today. I'm interested in applications from electromagnetics where you typically have quasilinear PDE constraints. So this is one class of problems I want to look at. And on the other hand, there's also applications where you're not interested in beautiful in standard inclusion shapes, but arbitrary inclusion shapes. We will also see applications of this later on. And in that case, I will show how you can use numerical approximation to get an approximation to this topological derivative, which also satisfies this topological asymptotic expansion to some extent, and which you can use in your algorithm. Okay. In order to do that, I will now illustrate how I would compute a topological derivative and show you where we get problems with arbitrary inclusion shapes, for instance. For that purpose, I will define a linear model problem. So this is the simplest possible non-irrelevant PDE-constrained topology optimization problem, I would say. So we're given a linear cost function. This happens to be the same function f as on the right-hand side of the PDE. So this is actually a self-adjoint problem, which I will not exploit. And we have a Poisson type equation with a diffusion coefficient, which is piecewise constant. And some right-hand side function f. This is the problem we will look at. The perturbed configuration then looks as follows. We fix a point C without loss of generality for now in the blue part, so in D without omega. And then beta omega epsilon is defined as before, but now for the perturbed domain. And this also gives rise to the perturbed state equation, which you can state for any small epsilon greater or equal to 0. With this setting, we can also set up a Lagrangian function that is just the cost function plus the PDE constraint, the perturbed PDE constraint. So it's a Lagrangian that depends on the small parameter epsilon and two variables, which stand for the state and the joint state later on. And we also see immediately, of course, if we plug in epsilon and u epsilon with the same epsilon, where u epsilon is the solution to the perturbed state, that the perturbed cost function value can be written in terms of the Lagrangian. Okay, so this is a simple model problem, which I will come back to later. Now I want to introduce a way of computing the topological derivative, and this is an abstract setting now, so not relying on the model problem I introduced before. I just wanted to show you this in order for you to have a feeling what this Lagrangian G can look like. Now imagine we're given the Lagrangian for a general PDE-constrained topology optimization problem. We're interested in the topological derivative, so in the difference of the perturbed and the unperturbed configuration. I will denote by u the unperturbed state, so I will not write u0, just u. As we've seen before, I can write the cost function in the perturbed setting and unperturbed setting in terms of the Lagrangian in this way. And for the third argument here, I already inserted a joint variable, which will come clear later. For now, it doesn't matter, but we will see in a second why we need this. This is the definition of the adjoint variable as usual. So let me now do some manipulations on this. So first we just add and subtract the two terms in the center. So we just add a 0. Next we use the fundamental theorem of calculus for the first difference. So this can be written as an integral over the derivative with respect to the state of a convex combination of u and u-eps. The third and fourth term remain the same. Then we add another 0, that is this term and this term. They add up to 0. And we subtract another 0, which is this term. This term is 0 due to the definition of the adjoint. Here it was important to use the adjoint as the third argument, because otherwise this term wouldn't be 0 and we couldn't have added it. Okay, so I've reorganized this difference of the unperturbed and the perturbed cost function in this way. And now it's easy to see that if for each of these three blue lines, the corresponding limit exists, then the topological derivative exists, and that's the statement of this theorem. So if these three limits exist, then the topological derivative is given as the sum of the three limits. This result is actually based on a result of Michel de Dufour from 2018, and Kevin and I kind of modified it a little bit for this setting in a paper from 2020. I should mention here that this is one way of computing topological derivatives in a Lagrangian way. There are other ways, for instance, one by Samuel Amstutz. However, I want to mention also that what is unique to this way is that we don't use a perturbation of the adjoint variable. So this only uses the unperturbed adjoint. This is different in the approach of Samuel and also in the approach of Kevin, which uses an averaged adjoint. This is slight differences, but also I have to mention that actually with this approach, you have the most restrictions in terms of the cost function. Also, certain cost functionals cannot be treated in this direct way, which can be treated using one of the other ways. If you're interested in a more detailed comparison of those three approaches, you can look into this very nice review of Kevin and Philipp Baumann, where they compare first and second order topological derivatives using those three approaches. Okay, so coming back to our model problem. Maybe let's have a brief look at the three terms once more. The third term here denoted by R0, I denoted by R0 because it's something like only a partial derivative. It's only a perturbation in the geometry, in the epsilon parameter. So this is a more standard term, and the other two terms, they actually involve the variation of the state, u epsilon minus u0, and these usually involve a bit more work. For the first term, we see that it's the difference of linearization with respect to u, in particular for our model problem, since both the cost function and the PDE constraint are linear, this one vanishes, so we don't look at R1 just for simplicity to reduce the amount of details. So we don't deal with R1. R0 is easy to deal with. So R0 would look like something like this, an integral over the inclusion of gradient u times gradient p, dividing by the volume of the inclusion. That by an application of the mean value theorem just gives the point evaluation of gradient of state and adjoint, which is this term. And of course, I should mention that we always assume that we have enough regularity such that these point evaluations exist. What's more interesting is the term R2, which I now want to develop in a bit more detail. So for the model problem, it would look like this. It involves the integral over the inclusion of the gradient of the difference between the perturbed and unperturbed state. And what we do in order to evaluate this term is we introduce a change of variables. So that means this is the perturbed setting that we saw before. We now do a change of variables, meaning that we shift the origin to be inside the inclusion. So the inclusion is now not around the point z, but around the point 0. And we divide everything by epsilon, meaning that the inclusion, which was an inclusion of size epsilon before, is now an inclusion of size 1, and the domain is blown up accordingly. If we do this change of variables, t epsilon here, we just get this. And then we do one more step, that is we apply the chain rule for this term, which gives us an additional 1 over epsilon. And then rewriting this, we can rewrite it in this form, where we introduce the quantity that I call k epsilon. And k epsilon is now the variation of the state variable u epsilon minus u0 after rescaling and division by epsilon. Okay, so R2 can be rewritten in this form. So far we haven't done anything, we've just rewritten the same term. But why did we do this? We're interested in what happens when epsilon is going to 0, and for some reason this rescaled version, this is useful for our approaches, for our approach. So what does it mean if epsilon is going to 0 now? Yeah, so this is for now. For now, we assume that there exists a function k such that k epsilon converges weakly. So the gradient of k epsilon converges weakly to the gradient of k. If such a function exists, then we can show that R2 epsilon converges to this term, and we're done. The question is, what is this k? And can we actually show such a convergence result? And here, in terms of the pictures, what does it mean in this blown up setting when epsilon tends to 0? That means that the outer boundary tends more and more to infinity, and we approach a problem on the unbounded domain with an inclusion of unit size in the center. So the equation that is satisfied by this k, we will see, will satisfy a problem on this geometry. That's the next result. We can show actually that this k epsilon converges strongly. So here we only need weak convergence, but you can also show strong convergence in L2 to the gradient of a function k, where k is the solution to this exterior problem. So it's a problem defined on this unbounded domain with this material distribution. That's denoted by this beta little omega here, where on the right-hand side you have the an integral over the inclusion involving the gradient of the state at the point of evaluation. Okay, yeah, so this is actually the main part in computing topological derivatives for PDE-constrained topology optimization problems. You have to show such a convergence result. If you have such a result, then you're basically almost done. You can state that the topological derivative is given like this. I can briefly show one way to prove such a convergence result. So there are different ways of doing this, and often this is proven by application of the fundamental solution of the Laplace operator. We want to avoid using the fundamental solution because we want because the proof I will show you actually also applies in the more general setting of quasilinear PDEs where you don't have access to the fundamental solution. And here the idea was the following. I will be very brief. So we want to show that k epsilon converges to k. So typically, as in any error estimates, you just proceed by setting up the equation that is satisfied by this difference. And then typically, ideally, we would like to insert the same difference as a test function and then estimate the left-hand side to the bottom and to below and the right-hand side to above, divide by one instance of the norm, and then you're done. However, this is not possible here since the function k epsilon minus k is not a valid test function. We have to work a bit harder, and the way we do this is we do splitting. We introduce another term, which we denote by k epsilon hat, which is the projection of k onto the unbounded, onto this blown up but bounded domain. I don't want to go into detail maybe, but this is the key idea. You introduce this projection. For this projection, you can show that it converges to this k in the suitable sense. And then you can rearrange this equation with the triangle up here in such a way that that you estimate k epsilon hat minus k epsilon. And here you can now insert k epsilon hat minus k epsilon as a test function and do the standard trick and get that both parts go to 0. And yeah, so this is the idea of the proof, to introduce this projection here. Okay, so this was the case for a linear problem, but as I said, we're interested actually in quasilinear PDEs, and actually we did this proof also for the quasilinear case, and this was just a simplification right now to the linear case in order to reduce technicalities. So in this paper we extended this, or we did this for the quasilinear H1 setting, as it is the case for two-dimensional models of electric machines, which I will show later on. We also did it in the case of 3D magnetostatics, which corresponds to 3D electric machines, and also for surface PDEs, but I think here we used a different method, the average joint method. Side remark. Okay, so now let's assume we know that we know this asymptotics result, so we know this convergence of k epsilon to k. So we, as I said, then we have a formula for the topological derivative, which would be the second line here, which, however, still includes the solution of an exterior problem. And in particular, it's also this exterior problem actually depends on the point of evaluation. So this is, at a first glance, a big restriction. So we need to, this is something we definitely have to think about. In the standard setting where you have a linear PDE constraint, like the model problem I introduced, and a disk or ellipse shaped inclusion, you can show, you can compute a closed form formula for the solution to this exterior problem, which is nice. Then you can just plug it in and really get a closed form formula for the topological derivative. So this is what I was talking about earlier. So in this case, it is possible, but it's not the case in general. So in particular, if you have different inclusion shapes, and later also if you have quasi-linear PDE constraints, this is not possible. But what you can do here is you can approximate this exterior problem in the following way. Namely, we realize, for instance, in this example, we realize that the solution k decays towards infinity as x to the 1 minus d. So that means, in particular, if we cut off this unbounded domain at a certain large enough distance, the error that we make might not be too bad. And that's the basic idea, that we truncate the unbounded domain at a certain radius r that is larger than 1, but doesn't have to be too large in practice, and solve for this exterior problem, which is now not an exterior problem anymore, solve this problem numerically by finite elements. This can be done. In particular, in the linear case, we just have to do it for the basis vectors of Rd, being here on the right-hand side in place of this eta, and then we can evaluate k of eta for any vector eta, and we can evaluate the topological derivative for any point z. So this is nice. So we only need 2 or 3 pre-computations in the linear case, and we can work with it for arbitrary inclusion shapes. In the case of quasi-linear PDEs, this is a bit more involved. In the worst case, you may have to sample the d-dimensional space, so the space of all possible values of gradient u of z. But in some applications, you can actually reduce it to a one-dimensional sampling, as we'll mention later on. So in principle, in quasi-linear case, the procedure is applicable, but may come with a large amount of pre-computations that you have to do. Okay. Yeah, we actually showed this procedure for a very general class of PDE-constrained problems, the most general class of elliptic problems, I have to say, that we could think of. Anything that you can write in this form, including linear and nonlinear PDEs in scalar and vector valued case, in particular also nonlinear elasticity case in 2 and 3 space dimensions. So this was a we did formal computations, so we didn't do the proofs for the asymptotic analysis. But if you formally assume that everything works as usual, then you can get a formula for the topological derivative, which you can approximate numerically, and we did this for a set of test examples and verified numerically that the expected rate in this topological asymptotic expansion is obtained. And if you're interested in the details, the sum of all of these terms is the topological derivative for this general setting. The K equation is here on the bottom, and maybe you don't, so it's hard to tell from here, but I want to mention that it's also a quasilinear PDE here. Okay, so let's come to some applications. So the first application I want to mention is topology optimization of an electric motor, in particular with multiple materials. So we're given a design of an electric machine, like depicted here, in a two-dimensional setting. So typically in electric machines, it's enough to just consider a two-dimensional cross-section. And this two-dimensional cross-section consists of different materials. Red here means some ferromagnetic material, which has nonlinear material behavior. Blue means air, and those yellow regions are permanent magnets, which are magnetized in given directions indicated by the arrows here. So the mathematical problem looks like this. We want to minimize or maximize a given cost function, for instance, the torque of the machine. The torque depends on the gradient of the solution U to this nonlinear diffusion equation, which is the equation of 2D magnetostatics. So it's a nonlinear Laplace type equation where you just have to note that this diffusion coefficient is a nonlinear function of the gradient of the absolute value of the gradient of the solution. Okay. Here U is just the potential, and the curl of 0, 0 U gives the magnetic flux density, just for physical interpretation. And what we want to do is now we want to find the optimal distribution of material in the inner part here. And we want to allow for different materials, that is ferromagnetic materials, the red one, omega F, and air, which is the blue one. And we also model the different magnets with different magnetization directions as different materials. So for instance, we will allow for 8 different magnetization directions, which gives rise to a problem where we want to distribute 10 different materials. Okay, the way I want to do this is by means of a level set algorithm. So first, a level set algorithm for 2 materials can be defined in the following way. You have a level set function that maps from your hold-all domain D into the real numbers. And whenever this level set function is positive, you're in one subdomain. Whenever it's negative, you're in the other subdomain. You can then define, let's call it a generalized topological derivative, which is the topological derivative from material 1 to material 2 inside omega 1, and the negative topological derivative from material 2 to material 1 in the other subdomain. And Samuel Amstutz and Heiko Andre in 2006 showed that with this you can run an algorithm as it is written here. So basically you just update your level set function psi k by this generalized topological derivative to give psi k plus 1. I will not talk about the details here, which is a quite widely used algorithm for topology optimization. You can also extend this to the setting of multiple materials. In that case, you would not consider a scalar valued level set function, but a level set function that maps not into R, but into Rm minus 1, if M is the number of materials. And similar as here, in the 2 material case, you basically split the line, the real line into 2 half lines. If psi of x is in the right half line, if psi of x is positive, you're in omega 1. If it's in the other half line, you're in omega 2. And the same idea carries over in this multi-material setting where you just divide the Rm minus 1, think of R2 in the case of 3 materials. You divide the R2 into 3 sectors, and each sector corresponds to 1 material. So this is a way to represent m materials by a vector valued level set function. And if you then define, again, this generalized topological derivative accordingly, and I just mentioned that this is related to the normal vectors pointing into these sectors, which is also the case here, by the way. The minus is actually the normal vector pointing into the negative numbers. If you do this accordingly, then you can run the same algorithm with an arbitrary number of materials. And okay, one more slide of details. Of course, you need all kinds of topological derivatives from material I to material J. In our particular application, we have 10 materials, so we need all combinations of different materials, from ferromagnetic material to air, to magnets, to magnet 1, to magnet 2, and so on. All of these formulas include solutions to exterior problems, so you need to pre-compute quite a few of these exterior problems. This is the K equation in the case of this quasilinear PDE. However, you can do this. You have to sample. Yeah, in this case, actually, you can use the structure of the problem in order to reduce the sampling from d dimensions to 1 dimension. Details can be seen in this paper. Yeah, I will skip the details and show you the numerical results. So as I said, we want to optimize with respect to iron, air, and 8 different material, 8 different magnetization directions with these angles. And in addition, we have a constraint on the magnet volume and also mechanical stress constraints, right? Okay, and here there should be an animation which is not working, but nevertheless, I put the initial and the optimized design next to each other. We start with all air, so with zero knowledge about the problem, and end up with an optimized design like this with very good performance, actually much better performance than the original design that we got from the industrial partners. So here we can see that only 4 of the magnetization directions appear because the other directions don't make sense in this region of the motor. Okay, yeah, this is joint work with my PhD student, Nepomucren, actually work in progress. We also extended this to the case where so right now we defined the different magnetization directions. We also extended it to the case where we don't know which magnetization directions are useful and where we try to find the optimal magnetization directions in the same optimization run. Okay, I don't know how much time I have left. Here, yeah, a few more minutes. I'll be rather quick on the second application. It's just an application where I want to illustrate, or where it was useful to have topological derivatives with respect to triangular inclusion shapes. So the background is a discretized material optimization problem. So imagine you're given a topology optimization problem. You discretize it by finite elements on a triangular grid. Forget about your continuous problem and just treat the discrete problem. So your functional is a function of a vector lambda in Rm. M is the number of triangles, where you have some bounds on it. And what is done typically in structural optimization is that you have some iterative, some sequential approximations of this hard problem. So you approximate the hard problem by simpler problems. You approximate J by J hat. And then the question is how you define these models, J hat. And there are different methods around. The most prominent one is probably the method of moving asymptotes, MMA, where you have sequential convex approximations. Here we suggest an approximation which is not necessarily convex, which is separable. Separability is important in order to have such that these sub-problems can be solved easily. And yeah, actually in this preprint, we investigated different models and compared different models. One of them is a model based on the topological derivative. Here, this graph basically just tells you, I will not explain it in detail, but if you take a model that is based on the closed form formula of the topological derivative, that is for ball-shaped inclusions, then you get this line up here. The truth are these crosses, which you might not see here. So the black line is the truth. This is what you get with the closed form formula. And if you do the work and do it with topological derivatives based for triangular inclusion shapes, with the right triangle shapes, then you get very, very close to the truth and get models that are very good approximations to the truth. This was an application where triangular inclusion shapes were important, and this method can also yield better local minima, but this is not the point of this presentation now. And finally, one last application from mathematical imaging. This is ongoing work with Boshra Miri from RIKEM and Ottmar Scherzer from both RIKEM and University of Vienna. We're looking at a Mumford-Shah type functional, or is it? I think it is the Mumford-Shah type, the Mumford-Shah functional. Ottmar Scherzer and co-workers worked on this problem a few years ago. They used the topological derivative with respect to a very with respect to a particular inclusion shape that's very thin ellipses. Actually, they have different dimensions in terms of epsilon in both directions, but they use topological derivatives with respect to these very thin ellipses in order to detect edges in images. Like here, you can see this parrot picture and what they get by their image segmentation based on these topological derivatives. The goal in the current study is to extend this to corner detection, because now we can not only deal with very thin ellipses or very thin bars, but we can deal with arbitrary inclusion shapes that also includes corners, for instance. Okay, so for this cost function, I wrote down the first order and second order topological derivative. Detail here is this animation is working, and then we pre-computed the exterior solutions K for the first and second unit vector for the basis of R2 for a large number of different inclusion shapes, namely all kinds of angles that we could get by discretizing the range of angles in this way. So we had a total of 135 inclusion shapes, for all of which we pre-computed the exterior problems. And so we have access to both the first and second order topological derivative for all of these inclusion shapes. Then our algorithm consists in the following. So this is a very simple image, of course, but the algorithm then basically just consists in computing the topological derivative with respect to all of these inclusion shapes that we saw and asking which one of them is giving the most negative value. And the answer in this case was, okay, this inclusion shape gives the most negative value, and this is the image. This is the image of the topological derivative on this image. So basically it says that it's most negative here along this edge, which is a good indicator that there should be an edge, which of course is true if you look at the picture, at the image on the left. Same second best option, it says it's a vertical. Third best option is a horizontal line, which detects all the other edges in this very simple picture, of course. Then we asked what is the inclusion shape that gives the smallest value of second order topological derivatives, and it told us it's this inclusion shape, so this angle. And if we look at the picture of the second order topological derivative over the image, it says at this location there should be an inclusion of this form, meaning that it detects a corner of this type up here. And second best option would be this inclusion on the bottom right, which makes sense. Third best option up here, this one. Fourth best option, this one. So in this simple application, it seems to detect the corners very well, which was a nice result for us. We even went a step further to do triple junctions. For this image, it also detected that here in the center, there should be a triple junction of this type. which is also true here. Okay, so this is work in progress. We still need to include this in a good and efficient segmentation algorithm such that we can get both edges and corners or triple junctions, but the first results are promising. Okay, with that, I'm coming to the end. Yeah, I showed you an overview over computations of topological derivatives for different classes of PDE-constrained topology optimization problems, including quasilinear PDE constraints and in particular also inclusion shapes that are non-standard. By approximating the topological derivatives numerically, we could use these quantities in, yeah, on the one hand, topology optimization algorithms, and on the other hand, in imaging example. So with that, I hope I didn't take too much over time, and yeah, thank you very much for your attention.